and they're the first and second law of thermodynamics uh, that govern all the stuff in the universe. And the first law of thermodynamics states that matter and energy can't be created or destroyed. They can only be converted one into another. And that's just another way of saying that I can't wave a magic wand and wish something into non-existence, and by the same token, I can't create something out of nothing. And then there's the second law of thermodynamics, which states that the universe tends towards maximum entropy. Now, you might not have heard that term before. How can we restate that in a way that makes sense to our everyday lives? And essentially, this is a way of saying that if you don't do anything, that the elements in a system, in a situation that you're looking at, are going to become more disordered over time. And the reason for that is that given the chance, um, elements, energy, whatever, are going to try and take the easiest way out of a situation or the lowest energy state. And you can demonstrate this to yourself by putting a drop of food coloring in a glass of water. If you wait long enough, what will happen is that the food coloring in the water will get to their lowest energy state, meaning that they'll become as randomized as they possibly can. This applies to any situation. There are always going to be situations in which there's a number of different ways that elements can be in a relationship with each other, but if you don't put any energy into the system, that relationship is always going to be the lowest possible energy, and that's what the second law of thermodynamics means. So the first and second laws govern all the stuff in the universe, and there's nothing we can do about it. And chemistry um, has to deal with these two laws of thermodynamics, and I'll show you how and why that happens as we move through the chapter. So let's talk about elements. All forms of matter are composed of elements, which are substances that can't be split into simpler substances by ordinary chemical means. Elements are given letter abbreviations that are called chemical symbols, and there are elements in our body that are present in both large and small amounts. Now, let's take each of these piece by piece. We're going to see in a minute that there's a chart that describes all the stuff in the universe, and it's called the periodic table. And it basically tells you what the atomic structure of all the elements are. And it also, most importantly, describes what we would call the fundamental particle, which is the tiniest piece of something that you can have and still have it react chemically like a larger amount of that particular thing. For instance, if you have one atom of carbon, it's going to chemically react the same way as a pound of carbon would. It's going to interact with other matter in the same exact fashion. This was a concept that was actually came to us from the ancient Greeks. A guy named Democritus was sitting around one day looking at a rock, and he reasoned that he could split that rock in half and split those halves in half again and again and again. And eventually he would get to a fragment of that rock that was so tiny that he couldn't split it any further. And he called that the atom. Okay, it comes from the Greek a meaning not and tomos meaning divisible. So this is a concept that's been around for a long time, and it's essentially the same concept that exists today when we think about the atom. And we'll talk in a minute about the structure of the atom. Elements are given abbreviations that are called chemical symbols, and these are usually a capital letter and often followed by a lowercase letter. And it's essentially the first few letters of the name of that particular element in most cases. In some cases, those are the English names, and in some cases, those may be the Greek names, and we'll talk about when that happens. Trace elements are present in tiny amounts in the body. Now, just because an element is present in small amounts in the body, that doesn't mean that it's unimportant. As an example, take the element iron. Okay, iron would be described in the periodic table this way. Let's use black, green for iron, red, blue. iron's atomic symbol is Fe, okay, and that comes from the Greek, okay, ferrium, and it is a trace element in the body. But if we were to remove all the iron from your body um, in one fell swoop, in one magic blink of an eye, you would die because your hemoglobin wouldn't be able to carry oxygen, and your cells wouldn't be able to generate energy because a very special metabolic pathway called the electron transport chain would shut down. So these trace elements are important to our existence. We absolutely need them. The units of matter of all chemical elements are called atoms. An element is a quantity of matter composed of atoms of the same type. Atoms contain a nucleus, a central region that contains two fundamental particles, the proton, which has a positive electrical charge, and the neutron, which has no electrical charge. And they actually make up most of the weight of an atom. The electrons have a negative electrical charge, and they orbit the nucleus in at varying distances from the nucleus, various fixed distances. They have very little mass, but the number of electrons in an atom and the number of protons in an atom are always the same. Okay, let's write that down. Let's put a line here, and I want to say always equal. I know my handwriting's not that good here. What that means is that every atom of an element is electrically neutral. It has no net charge. Okay? So let's look at the Facebook of the elements. This is the periodic table. If you get a chance, or if you're interested, I can print you out a large color version of this, or if you have access to a color printer at home and you get to this slide in the PDF, you might want to blow this particular chart up, because this is essentially a description of all the matter in the universe. All the matter in the universe falls into one of these categories here contained in this very tiny chart. Okay. Now you'll notice that the chart is arranged in columns and rows, and there's a reason for that. Essentially, the chart goes from small atomic mass to large atomic mass as you go from left to right. Let's see here. Let's do left to right. And let's go with black here. Okay. So atomic mass increases as you go in this direction. Okay. And atomic mass also increases as you go from top to bottom. Okay, so the heaviest elements are going to be in the lower right-hand corner of the table, and the lightest elements are going to be in the upper left-hand corner. Now, what's the significance of going from left to right? An increase in atomic mass. Basically, as we go from left to right, we're increasing the number of protons and neutrons in the nucleus. As we go from top to bottom, we're also increasing the atomic mass, but we're doing it in a more substantial way. We're actually adding an electron orbital, a shell, and so we're adding several protons and electrons at the same time as we go from top to bottom. Now, what's the significance of these numbers here? Okay, these, you see these little 1A, 2A, and all that. Okay, what those are the number of electrons in the outer shell of the atom, and we'll get to the atomic structure in a minute. The reason that these numbers are important is because it's the number of electrons in the outer shell of an atom that tell us what kind of chemical reactions those elements are going to engage in. Okay, so if we look at all the elements in this column, they have one electron in their outer shell. All the elements in this column have 2. Over here, 3, 4, 5, 6, 7, and 8. Now, you might notice that we don't go beyond 8. And there's a reason for that. And the reason for that is the way that the electrons fill the shells as we try and load up the atom, as we go from light atoms to heavy atoms. And essentially, the first shell, the first set of electrons that orbits an atom, you can only have 2 electrons in the outer shell, and all the remaining shells can have a maximum of 8 until you get up to some of the really big shells where the number expands significantly. But we're not going to have to worry about that because we're only going to deal with these elements that can manage to pack a maximum of 8 in their outer shell. In a chemistry class, you might deal with some of these atoms that have more than 8 in their outer shell, and those guys are in these yellow blocks down here, these heavier atoms in this middle portion of the table. And we don't worry about those much when we talk about the chemistry of living systems. Okay, so you can see here in each of these entries in the table that you've got a capital letter, okay? And then if you look real close, and I know it's tough on the video, but if you pull up a periodic table off of Google, or if you print out this particular slide as big as you can get it, what you'll see is that let's take carbon as an example. Okay, carbon has atomic symbol C. There's carbon right there. Okay, carbon has an atomic number of 6. Now, what does that mean? 6 tells you the number of protons in the nucleus and the number of electrons that are outside the nucleus. Remember that all elements are electrically neutral. And then carbon has an atomic mass of a little bit more than 12, 12.01. Okay. Now, what is the atomic mass? The atomic mass is basically a count of the number of protons and neutrons in the nucleus, because remember that the nucleus contains most of the weight of an atom. The electrons have virtually no weight whatsoever. So when you look at carbon, when you look at this entry in the periodic table, you immediately know several things about the structure of the carbon atom. It has 6 protons in the nucleus. It has 6 electrons orbiting the nucleus. And it has 6 neutrons in the nucleus as well. And you get that by subtracting the atomic number from the atomic mass. Now you might wonder why this number is not perfectly 12. It's a little bit higher than 12. And the reason for that is that when all the stuff in the universe was made, some of the elements were a little bit heavier than others, even though they were chemically the same, meaning they have the same number of protons in the nucleus and the same number of electrons orbiting the nucleus. The extra weight in certain of these variations on an element comes from additional neutrons in the nucleus, and they're called isotopes. I-S-O-T-O-P-E-S, isotopes. Okay. Now these isotopes will react chemically just like the quote-unquote normal version of the element. However, they've got a little bit more atomic mass. Now some isotopes are what we call unstable, meaning that they will break down over time and form different elements, and those are called radioactive or unstable isotopes. And some isotopes are stable, meaning that they just kind of hang out the way they are for the rest of time. The reason that isotopes are important when we talk about medicine is that isotopes that give off radiation that are unstable isotopes are often used as tracers to try and visualize chemical processes inside the human body. For instance, you can give radioactive tracers to look at the structure of the gastrointestinal system. If you use, for instance, a solution of barium, you drink barium and they visualize the esophagus, the stomach, the small and large intestine, and so forth. The barium will chemically react just like normal barium, but it also gives off a form of energy that we can trace using an instrument, and that allows us to visualize structures inside the body. For instance, another application of isotopes is the use of radioactive carbon. Sometimes we use radioactive carbon and we visualize activity inside the brain in a procedure called a PET scan, where essentially we provide radioactive glucose, which is a carbon-containing compound, but because it gives off um, energy in the form of electromagnetic radiation, we can follow where the glucose goes and we can ask questions about the way the brain functions. Okay, so that's the significance of isotopes in a clinical setting, and that's why we want to be aware of them. And that's why these numbers are not, perfectly round numbers. That's why they have figures after the decimal point, is that these heavier versions of the same element will skew the average weight a little bit higher than you would expect. Now, there's a couple of different ways to read this bottom number, this atomic mass. One way to read it, and an easy way to kind of get this in your head, is that 1 mole of carbon weighs 12.01 grams. Now you might say, well, wait a minute, what the heck is a mole? The only mole I've ever heard of is a little furry creature that burrows underground. Well, a mole is just a count, okay? Mole, M-O-L-E. Okay, like a dozen is 12. A mole is a very large number, okay? And it's equal to 6.02 times 10 to the 23rd. Okay, so that's a large number. It's a large count, okay? And what we're saying here when we look at this bottom number, this 12.01, is that 6.02 times 10 to the 23rd atoms of carbon weighs exactly 12.01 grams. Now this is useful if you're a chemist, because this tells you that if you weigh out a certain amount of something, okay, a certain number of grams of an element or a compound, that you can basically compute how many atoms of that compound or how many molecules of that compound you've got. And that helps you when you set up chemical reactions. Okay. Another way to use this bottom number is for the weight of a single atom. Okay. If you look at a single atom and you look at the atomic mass, you can say that a carbon atom, the most abundant isotope of carbon, weighs 12 atomic mass units per atom. Okay, but the thing about that is, if you're a chemist, it's real hard to weigh a single atom of something because we really don't have those kind of instruments. And this is why the mole concept was developed, as a way to sort of be able to work with things on an instrument like a balance or a scale, and be able to set up chemical reactions in a test tube or a beaker and make a certain amount of product. Okay, so that's what the periodic table is telling you. Okay, you could think of it as the Facebook of the elements, if you like. So let's look at the structure of an atom. Now, you got two models of an atom here. One is the electron cloud model, and one is the electron shell model. And what they are representations of what we know about the atom up to this point. And what I'd like to talk a little bit about here is just science in general, and the way science in general likes to deal with information that it collects about certain phenomena is to make a model that represents the state of knowledge of that phenomenon at the time. And our model of the atom is not perfect. Okay, this is just the best version of the atom that explains all the information that we know. Okay, if we look on the right, this is a fairly straightforward model. What you can see is that the protons and the neutrons are here in the nucleus, and they make up most of the mass of the atom, and that the electrons orbit the nucleus like planets around the sun. Okay, here's the first electron orbital with 2 electrons in it, and here's the second electron orbital, which in carbon has 4 electrons in it. It can hold up to 8. Now, is this model of the atom a perfect model? And the answer is no, because there are aspects of atomic behavior that don't obey this model. The electron cloud model over here is probably a more accurate representation of what we understand about the atom. And what it's showing you is that the atoms don't so much orbit the nucleus like a planet orbits the sun, but they're basically at a certain distance from the nucleus in a three-dimensional pattern, okay? And it turns out that the orbitals that we're dealing with, they sort of are shaped like a globe or a sphere around the central nucleus. The problem, of course, with this model of the atom is that it's really hard to work with on a piece of paper, right? Because these atoms, you can't really see them. They're moving around in here, but they're moving so fast that we can't really take a snapshot of them. And this is just a representation of where they're most likely to be. This model of the atom is easier to work with in terms of trying to set up chemical reactions, as you'll see in the next few slides. And so we use both of these models to explain certain aspects of atomic behavior that we've gathered over many decades of research into the structure of the atom. But something that you'll notice about both of these models is that there's something about these models that is kind of doesn't make sense. Okay, remember we talked about the fact that electrons have a negative charge and protons have a positive charge. Well, just like with magnets that you may have played with when you were younger, there's a plus and a minus side to a magnet. If you've ever tried to get the two positive sides of a magnet to go together, they'll push on each other. The same with the two negative sides of a magnet. So like signs repel, and that's the same in electrical charge. Electrical charges of similar sign will repel each other, and electrical charges of opposite sign will attract each other. And you know this from playing with magnets as well, right? When you get the plus and the minus end of a magnet next to each other, they will attract each other very strongly and be very difficult to pull apart. So if you look at this model of the atom, it kind of, in a way, doesn't make sense because you notice that the electrons have a negative charge and the nucleus has a positive charge because of all the protons that are in there. And so this model should either collapse or explode. And we know that atoms don't do that, generally speaking. So there's something about the behavior of the atom that we don't understand. And you might ask, well, what explains this? And the answer we have up to this point is we have no idea. There's a lot about the atom that we're still trying to discover, and we may not know the complete picture of atomic structure within our lifetimes. So when you see science proposing a model for anything, what you have to do is always take it with a grain of salt because science is always learning new things as new experiments are performed and as new information becomes available, and that modifies our model of the atom. But for our purposes, what we'll work with is this model of the atom here. Whoops, sorry about that. This model of the atom here on the right-hand side with the electrons easily visible, okay, the electron shell model, and that's just for simplicity's sake, okay? And let's talk a little bit about atomic structure, okay? The atomic number, remember, is the number of protons in the nucleus and the number of electrons orbiting the nucleus. So remember, we gave the example of carbon, right? Carbon has an atomic number of 6, meaning that it has 6 protons in the nucleus and 6 electrons orbiting the nucleus. Well, the mass number is the sum of the protons in the nucleus and neutrons added together in the nucleus. And so for carbon, that number was 12. 6 protons and 6 neutrons in the most abundant isotope of carbon. And we already discussed how that's represented on the periodic table. Okay, so let's look at some atoms and their atomic shell models. Okay, so here you can see hydrogen, the simplest atom, with a single proton in the nucleus and a single electron orbiting it. So hydrogen is made up of 2 particles. One has a negative charge, one has a positive charge. The net charge on hydrogen is 0 because the negative charges cancel out the positive ones. Here's carbon, which we already have seen a couple of times. 6 protons and 6 neutrons in the nucleus, 6 electrons orbiting the nucleus. Here's nitrogen, 7 protons and 7 neutrons in the nucleus with 7 electrons orbiting the nucleus, 2 in the inner shell and 5 in the outer shell. Okay, here's oxygen. Okay, oxygen has 8 protons and 8 neutrons in the nucleus and 8 electrons orbiting the nucleus, 2 in the first shell and 6 in the outer shell. Okay, now notice what's happening, that this first shell got filled up when it got 2 electrons in it, and the next shell didn't get filled up, as we're going to see, until we get all the way to the number 8, with 8 electrons being maximum occupancy. Okay, let's move on to some other elements. Here is sodium. Okay, sodium has 11 protons and 12 neutrons in the nucleus, and it's got 11 electrons orbiting the nucleus. 2 in the first shell, that first shell is now full. 8 in the second shell, that second shell is now full. And 1 in this third shell, which is a long way from being full. We can manage to fit a maximum of 8 electrons in this outer shell. But notice that the second shell was full when it had 8 electrons in it. So if you want to envision the atom as being like a hotel, what you've got are different floors with different amounts of occupancy on each floor, right? First floor has 2 rooms, each of which can fit an electron in them. Second floor has 8 rooms, each of which can fit an electron in them. And the next floor also 8 rooms, okay, each of which can fit an electron. So as you fill each floor, you have to move up to the next floor in order to get a room in the hotel atom. Here's chlorine. Chlorine has 17 protons and 18 neutrons in the nucleus, and it's got 17 electrons orbiting the nucleus, 2 in the first shell, 8 in the second, and 7 in the third. So this guy is almost at full occupancy. He only needs 1 more electron to be completely full. And here's potassium. Okay, potassium, 19 protons in the nucleus, 20 neutrons in the nucleus, and 19 protons orbiting the nucleus. 2 in the first shell, 8 in the second, 8 in the third, and 1 in the fourth. Okay, so notice something about potassium and sodium, which is kind of interesting, which is that if these atoms wanted to fill their outer shells, which is essentially what all chemical reactions are about, trying to fill the outer shell of an atom, it would be easier for them to lose an electron than to pick up 7 more, and that's exactly how they behave when they engage in chemical reactions. The same is true if you look at chlorine, right? If you look at chlorine, you've got 7 in the outer shell. Well, what's going to be easier for chlorine to do? Pick up 1 or dump 7? And the answer is to pick up 1. And so that governs the chemistry of chlorine. These guys over here, oxygen, nitrogen, carbon, and hydrogen, it's easier for them to pick up atoms. Okay, so carbon will pick up 4 electrons to fill its outer shell. Nitrogen will pick up 3, and oxygen will pick up 2. And when I say fill the outer shell, what I mean is come to an arrangement with another atom where by either handing electrons over or picking electrons up or sharing electrons, the outer shell becomes filled. Okay. Okay. Atomic mass we've already talked about. This is just a slide showing you different ways to compute atomic mass. Another unit of atomic mass is called the Dalton, which is equivalent to an atomic mass unit. The masses of subatomic particles are given here. Okay. Note that most of the mass of an atom is in the neutrons and protons. You can almost disregard the weight of the electrons. And note that the atomic mass of an atom is closest to its most abundant isotope, meaning if you were to go out, for instance, and collect atoms of carbon, most atoms of carbon would weigh 12 Daltons per atom, but some of them, the isotopes, would be a little heavier. And so if you took the average weight would be a little bit more than 12. Okay? There's just a little bit more discussion about atomic mass, also known as the atomic weight. We've already discussed isotopes and abundance The mass of a single atom is slightly less than the sum of the masses of its neutrons, protons, and electrons, because a little bit of the mass was lost when the atom's components came together to form an atom. Now, do we have to worry about this when we're just talking about basic chemistry? And the answer is no. Okay, basically what we have is the weights that come from the periodic table. Okay, a couple of more concepts. Okay, an ion. Now, this is very important. Ions are important in living systems because they can carry electrical signals around living systems. Now, what kind of tissues in the body make a lot of use of electrical signals? The nervous system and the muscular system, just to name a few. In fact, every living building block in the body, the living building blocks of the body are called cells, use electrical charge as a way to store energy, just like energy stored in a battery. And the way this happens is by arranging it so that certain ions are on the outsides of cells and certain ions are on the inside of cells. So what you have is a separation of charge across the outer layer of the cell, which is called the cell membrane, and that represents a form of stored energy. An ion occurs when an atom either gives up or gains an electron. If an atom gains an electron, it's called an anion, and it's going to have a negative charge next to it equal to the number of electrons that it picked up. If an atom loses an electron, it's going to have a positive charge, and it'll be called a cation, and it'll have a plus next to it and a number indicating the number of electrons that it lost. Now, what's an easy way to remember this? The way I always remembered this is that the key is that when you look at the word cation, okay, cation, C-A-T-I-O-N, the T in cation looks like a plus, okay? So that's how I always keep it in my head that cation means a positively charged ion. Now, why do ions happen? Why do ions happen? Ions happen because, as we saw with looking at some of the atomic structures of selected elements that we did a couple of slides ago, some atoms are going to be more stable. They're going to have a lower energy if they give up or pick up electrons than if they sit around in their regular electrically neutral state. Okay? Remember that in chemical reactions, it's all about having a full outer shell any way you can get there. We can give up electrons, we can pick up electrons, or we can share them. And any way that we can get to that full outer shell, that's going to represent a low energy state for us, and that'll satisfy that second law of thermodynamics. So any way we can do that, we're going to try and do it. A molecule is formed when atoms share electrons, and it's written as a molecular formula showing the number of atoms of each element. Now, sometimes the sharing is pretty complete. Sometimes an atom will completely give up an electron to another atom, and they'll be attracted to each other because of their opposite charges, okay? And that's called an ionic bond. And then sometimes an atom will come to an agreement with the neighboring atom where the electron spends some of its time with atom number 1 and some of its time with atom number 2, and that's called a covalent bond. Okay, covalent bonds are very, very strong, and we'll see how they're formed as we move through the chapter. A free radical is an electrically charged atom or group of atoms with an unpaired electron in its outer shell. They're unstable and reactive because they're trying to fill their outer shell by either giving up an electron or stealing an electron from another molecule. And when that happens, you can break chemical bonds. And very often when you break chemical bonds in an unplanned fashion, you produce damage in living systems. And that's why we want to stay away from free radicals inside living systems as much as we can, because they can screw up the molecules that allow life processes to occur. Antioxidants are substances that inactivate oxygen-derived free radicals. Oxygen is one of those elements that can form free radicals, which can steal electrons from other molecules and cause them to break down. And what happens with antioxidants is basically we kind of box up these unstable species and quit them from causing damage. So we kind of lock them in prison, so to speak. You may have heard that it's good for you to eat a lot of green leafy vegetables because they have a lot of antioxidants in them. And this is the idea, is that there are certain compounds, for instance, the fat-soluble vitamins, that can limit the damage that these free radicals can cause in living systems. And as a result, this is a healthy way of eating. Okay, let's talk about chemical bonds. The atoms of a molecule are held together by forces of attraction that are called chemical bonds. The likelihood that an atom will form a chemical bond with another atom depends on the number of electrons in the outermost or valence shell. Basically, all the action happens at the outer surface of an atom or molecule, right? That's where we're making and breaking chemical bonds. That's where we're generating novel compounds. And that's all chemistry is. If we wanted to define chemistry, chemistry is just the making and breaking of chemical bonds to form new compounds, new molecules. That's it. That's the sum total of what we mean when we talk about chemistry. So let's talk about some of these different bonds. Okay? An ionic bond forms when an atom loses or gains valence electrons. The positively and negatively charged ions are attracted to each other. Cations are positively charged ions that have given up one or more electrons, so they're what are called electron donors, while anions are negatively charged ions that have lost an electron, that have picked up an electron. They're electron acceptors. So remember that an anion, let's write this down, is going to have a negative charge. Let's put a negative sign here. And a cation is going to have a positive charge, right? Cation has a positive charge because it lost electrons to another atom. An anion has negative charge because it picked up electrons from another atom. So let's look at how ionic bonds are formed. And this is just the formation of sodium chloride. Now, you know sodium chloride better as table salt. You put it on your food, you eat it. But let's look at what goes into table salt. Let's look at sodium and chlorine, right? If we were to look at sodium, this is sodium up here. Sodium is a very dangerous and toxic metal. If I were to bring sodium into the classroom, I would have to have it under a layer of kerosene, because if sodium comes into contact with water, it'll explode and burst into flames. It's a very, very dangerous, unstable compound to have around. Chlorine, if you've ever been around a pool that's being chlorinated, is an extremely corrosive gas. If you were to get chlorine in your mouth or in your nose or on your skin, it would cause a lot of inflammation and a lot of damage. Yet when these two compounds come together, they form something that you eat every day without significant harm to your body. And so the point of this is that the properties of the elements change when they buddy up. Okay, they form something that has very different behavior in living systems and solutions and so forth than it does before it undergoes the chemical reaction. And you're going to find that that's true for a lot of chemical reactions, that the thing that you form is going to be fundamentally different from the components that build it. So let's look at this reaction, this chemical reaction. Sodium has one electron in its outer shell. And so the easiest thing for sodium to do, the activity that would obey the second law of thermodynamics, is to give up this outer electron, hand it off to another atom whenever that can be done. And so when sodium has the opportunity to do that, that's exactly what it'll do. It'll kick this electron out and it'll form the sodium cation. Now look at the sodium cation. 2 electrons in the first shell and 8 electrons in the outer shell. That's a low energy species. That's a low energy particle. And so that's a happy particle. That's a particle that satisfies the second law of thermodynamics. That's one that wants to form. And so by giving this electron up, we form something more stable than the parent element. Let's look at chlorine. Chlorine has 7 electrons in its outer shell. the easiest thing for chlorine to do is pick up one more and form the chlorine anion. Look at chlorine, right? 2, 4, 6, 7, okay? Full first shell, full second shell. That last shell really wants one more electron, and so that's exactly what it tries to do whenever possible, is pick up one more electron. And so what you can see when chlorine forms its anion, it fills this outer shell. And so this is another low energy species. Look at how the shells are filled. 2 in the first, 8 in the second, and now 8 in the third. That's a stable species. So when you get sodium and chlorine near each other, when they bump into each other, that's exactly what happens, is that sodium will give up an electron and chlorine will accept it, and it'll form sodium chloride. Now, look at these two particles, right? This particle has a negative charge. This one has a positive charge. What holds them together? What holds them together is the fact that they have opposite charges. So this is almost like a magnetic attraction, except it's what we call an electrostatic attraction. And that's what we know as table salt, okay? That's an ionic bond. Generally, substances that form ionic bonds tend to form crystalline solids. Okay, if you've ever looked at a salt crystal under a magnifying glass, you'll find that it looks almost like a perfect cube. And that perfect cube is kind of interesting because, and we'll see in a minute, that perfect cube is basically an interspersing of sodium ions with chlorine ions. On every side, a sodium ion is near a chlorine ion, and on every side, a chlorine ion is near a sodium ion. And that's the most stable arrangement of those charged particles, right? That's low energy because charges that are opposite in sign will attract each other, and that's what holds the crystal together. If we were to make all the negatively charged anions sit on one side of the crystal and all the positively charged cations sit on the other side, we have to put a lot of energy into the system to keep that together because they'd be pushing off on each other. And so that's an unstable set of molecular arrangements. That's not what happens when we just let things take their natural course. Okay, covalent bonds are different. Covalent bonds, what we do is we don't hand an electron over or pick an electron up permanently. We share electrons between adjacent atoms. Covalent bonds can form between atoms of the same element, and they can form between atoms of different elements. We can share 1, 2, or 3 pairs of electrons between these elements. A single pair of electrons forms what we call a single covalent bond. 2 pairs of electrons forms what we call a double covalent bond, and 3 pairs of electrons forms what we call a triple covalent bond. In terms of bond strength, a double bond is twice as strong as a single bond, and a triple bond is 3 times as strong as a single bond. Covalent bonds are common and are the strongest chemical bonds in the body. Covalent bonds can be polar or nonpolar. Now, what does that mean? Well, envision now that we have a connection between two atoms, and that connection is a pair of electrons. That pair of electrons is going to spend some time with atom number 1 and some time with atom number 2. If the two atoms are identical or close to identical, what we have is something called a nonpolar covalent bond, where the amount of time that electron pair spends with atom number 1 is exactly the same as the amount of time that it spends with atom number 2. In a polar covalent bond, what we have is a kind of an unequal sharing of that electron pair. The electron will spend more time with one atom than the other. It's kind of like a tug of war in which one team has a little bit more power than the other, and so they get the bulk of the rope, but the two teams are still connected to each other. In a nonpolar covalent bond, the two teams would be of equal strength. Now, why is this an important thing to know or an important thing to understand? Well, because when you have a polar covalent bond, what you have is a slight separation of charge in the molecule, okay? One end of the molecule is going to be a little bit negative, and one end of the molecule is going to be a little bit positive. The reason that that's important is because nonpolar molecules like to associate with other nonpolar molecules because that satisfies the second law of thermodynamics, and polar molecules like to associate with polar molecules for the same reason. Um, an example of a nonpolar molecule would be something like Crisco or vegetable oil. If you've ever been to the grocery store and you've picked up a bottle of Italian salad dressing off the shelf and you look at it, what you'll see is that the oil is on the top and the water and the salts and the spices are on the bottom. Well, the oil is a nonpolar molecule, and so it's going to want to associate with the other oil molecules, while the water and the salt are either charged or polar, and they like to associate with each other. And so if you don't do anything to a bottle of Italian salad dressing, it'll separate. If you take that bottle and you shake it, you'll temporarily mix those layers up. You'll form what's called an emulsion. But if you put that bottle back on the shelf and wait, the oil will separate out and the water and the salts will be on the bottom again. And that happened because of the second law of thermodynamics. That's the low energy arrangement of those classes of molecules. An easy way to remember this is like dissolves like, meaning that chemicals that have similar chemical properties like to associate with chemicals that share those properties. So polar things like to get with charged or polar things, and nonpolar things like to get with nonpolar things. That's the low energy state. So let's look at some covalent bonds. And here you can see some covalent bonds formed between atoms of the same element. These are nonpolar covalent bonds. Here's a single nonpolar covalent, a double nonpolar covalent, here in a triple, right? Hydrogen, oxygen, and nitrogen, respectively. Here's another example of a nonpolar covalent bond, this time formed between atoms that are different, okay, between carbon and hydrogen. This is the formation of methane. And what I'm going to tell you is essentially that if you look at your periodic table, okay, and the part of the periodic table we're interested in is the part towards the top, okay, and what we want to look at are the elements that are to the left of carbon in the periodic table and to the right of carbon in the periodic table. Basically, the elements that are to the right of carbon in the periodic table tend to try and pull electrons towards them more vigorously than carbon will, okay? And the elements that are to the left of carbon in the periodic table will tend to give up electrons. And so those elements that are to the right of carbon, things like oxygen and sulfur and chlorine, those and nitrogen, those are what we call electronegative elements. They have a lot of yank when they're involved in a covalent bond. Whereas the elements that are either right there with carbon or to the left of it are what we call electropositive elements, and they tend to give their electrons up. Now, in methane, what you've got is nonpolar covalent bonds, and the reason for this is that the difference in the amount of influence that the carbon atom and the hydrogen atom have over where the electrons in this bond spend their time is about the same, okay? So if you look at carbon and hydrogen, for instance, the strength of the two teams in this tug of war is about equal, okay? So there's not a significant separation of charge in any of these four bonds. So this is what we call a nonpolar covalent bond. But when we get down here to water, okay, H2O, what you see is a polar covalent bond. And the reason for that is if you look at the periodic table, oxygen is to the right of carbon. And so it has more influence over where the electrons spend their time than hydrogen does. And so you have an unequal sharing of the electrons in this bond. And the result is a slight separation of charge, where the oxygen is slightly negatively charged while the hydrogen is slightly positively charged. And that has consequences. And the consequences for water are that water is a polar solvent, meaning that the kind of things that dissolve in water are also either going to be charged or polar. And if you think about this kind of stuff that dissolves in water, it tend to be charged or polar compounds. As an example, okay, y'all know that if you take a spoonful of table salt and you stir it into a glass of water, it'll dissolve. Why is that? Because water is a polar solvent and sodium chloride is an ionic compound. Okay, remember, like dissolves like. You also can take a teaspoon of sugar and dissolve it in a glass of water very easily. And if you look at the structure of a carbohydrate, which is the class of molecules to which sugar belongs, what you'll find is that it's a combination of carbon, oxygen, and hydrogen, and that makes a polar compound. And so it's very easy for sugar to dissolve in water. The way you know that something's dissolved in something else is when the solution is clear. Okay? But there's also some things you know that can't dissolve in water. You can't, for instance, take oil and try and dissolve it in water, or Crisco and try and dissolve it in water. It won't work. It'll just sit there and float, okay? By the same token, if you took a teaspoon of salt and tried to dissolve it in oil, it wouldn't dissolve. It would just sit there at the bottom of the oil and look at you, okay? The charged stuff would stay with the charged stuff, and the nonpolar stuff would stay with the nonpolar stuff. And you can try this experiment at home. I'm sure you've done it 100 times, and you can see that what I'm saying is correct. Okay, so let's move on to polar covalent bonds. These are formed by unequal sharing of electrons between atoms. For example, in the water molecule, which we just saw, there's a slight separation of charge, and we indicate that using a special sign here. What we do is we have a little Greek letter, lowercase delta, and a negative, meaning partial negative, near the oxygen of water, and partial positive near the hydrogen of water. Okay, and so we would draw the water molecule like that. Okay, and we would put these little signs here to indicate, again, forgive my handwriting, the relative charges. Okay, so that's your partial negative. Let's put a circle around that to make that easy to see. That's your partial negative there, and that's your partial positive there. So this is a polar solvent. Okay, it has a separation of charge. Remember, because the oxygen has more yank on the electrons in this bond than the hydrogen does. Hydrogen bonds are a different kind of bond. A hydrogen bond really is sort of an electrostatic attraction between polar molecules that contain hydrogens that are bound to electronegative atoms. And the classic example of the hydrogen bond is the attraction of water to itself. So let's draw a couple of water molecules here. Okay, there's one H2O, and there's another H2O. Okay, and remember what we said about water, right? Water has a slightly positive charge on the hydrogens and a slightly negative charge on the oxygen. So there's your slight positive over here, and there's your slight negative over here. Now, in solution, when two water molecules approach each other, what happens is that they will kind of twist and rearrange themselves so that the slight negatives are near the slight positives, and the slight positives are near the slight negatives. And the result of that interaction, that weak attraction, is what we call a hydrogen bond. Okay, so let me draw these negatives and positives in here for you. And the way they usually show a hydrogen bond in your textbook is a dotted line. Okay. Okay. And that's an example of hydrogen bonds. And what that tells you is that polar solvents, polar molecules, are in a way attracted to each other because of their chemical properties. This causes water to be attracted to other water molecules, and this provides very special properties to water, one of those being surface tension. If you've ever walked by a creek or a pond in the summertime and you see those little insects that manage to do what Jesus did and walk across the water, but they do it using surface tension as a way to hold their weight up. Surface tension results in an upward force on the insect because the water molecules are more attracted to themselves than they are to the air above them, and that provides enough force to hold the body of the insect above the water. This is also what accounts for the fact that as water changes from a liquid to a solid, which we know as ice, that the solid is going to be less dense than the liquid is, because in a solid, what happens to the components of a solid, either the molecules or the atoms, is that there's very little movement. In a solid, essentially, atoms sit at a fixed point and they just kind of jiggle a little bit. They vibrate very slightly, but they don't move past each other. In a liquid, the molecules or atoms can move past each other. They have enough kinetic energy so that they can slide by each other without you having to do anything. That's why liquids form to the shape of their container. And in a gas, there's even more energy of movement, kinetic energy. And as a result, a gas will fill all parts of its container. Well, when water freezes, when it goes from a liquid to a solid, it has to arrange itself so that you've got this alternation of charges here. You've got the slight positives near the slight negatives and the slight negatives near the slight positives. And what that does is it creates empty space between the molecules, and that's why ice floats. And y'all know intuitively that ice floats in a glass of water. This also is the reason why when ice freezes, it expands. This is why, for instance, if you've ever left a can of juice in the car on a cold night, you'll come back the next morning and the can will have split open. And the reason for that is because the water inside it has expanded bigger than the container can hold, and the container will pop open. Okay, this is also why cracks in the sidewalk get bigger in the wintertime as the water in the cracks cycles between a solid and a liquid. Okay. Where else are hydrogen bonds important in living systems? Well, they're important for establishing links between molecules or between distant parts of a big molecule, and they also help to form molecules that have a three-dimensional structure, and this three-dimensional structure is held in place by these weak electrostatic interactions, these hydrogen bonds. Okay. These are weak intermolecular bonds. They serve as links between molecules, and they determine the three-dimensional shape of many molecules. They result from the attraction of oppositely charged parts of molecules rather than from the sharing of electrons. And in water, this creates cohesion and creates surface tension. An example in the health field, okay? If you've ever given blood and they do a finger stick on you, and what they do is they take what they call a hollow glass tube called a capillary tube, and they'll touch it to the drop of blood on your finger, and you'll see the drop of blood wick straight up the capillary tube. The reason for that is that glass is also a charged molecule. Silicon dioxide has a charge, and it's attracted to the water, and so the water will cling to the glass, and that attraction is enough to pull water up a very narrow channel. Okay, so again, due to surface tension. This is also how water gets to the tops of trees. Okay, the water is attracted to the living components of the tree, the wood, which is made up of sugars, which are polar, and as the water evaporates from the leaves, the surface tension, along with the evaporation, draws the water from the roots all the way up to the shoots. Otherwise, water would never get to the tops of tall trees if water was a nonpolar solvent. Okay. Chemical reactions occur when new bonds form and old bonds are broken. In the human body, we call all the chemical reactions that happen, regardless of what they're doing, metabolism. And metabolism is actually broken down into two broad classes of reactions: anabolic reactions, which build big molecules from tiny ones, and catabolic reactions, which break big molecules down into smaller ones. The law of conservation of energy states that the total mass of reactants is going to equal the total mass of products. And in a chemical reaction, what that means is that the number of atoms on the left-hand side of the equation has to equal the number of atoms on the right side of the equation. Okay, so this is that first law of thermodynamics coming into play again. And so whenever we look at a chemical reaction, we have to make sure that it's what we call balanced. So let's talk a little bit about energy and chemical reactions. The definition of energy is the ability to do work, to do something, to cause something to occur. Kinetic energy is what we call the energy of motion, okay, movement, and potential energy is energy that is due to your position, okay, as an example, okay, if you take the elevator at Antonelli up to the 6th floor, okay, in order to get up there, you had to have energy put into the system. That energy came from the electricity that ran the elevator that moved you, energy of motion here, from the 1st floor to the 6th floor, right? Now that you're on the 6th floor, you have potential energy, right? This is energy that is yet to be realized, but could be realized very quickly. If you were to jump out the window from the 6th floor, you would fall to the ground. That would be a conversion of that potential energy into kinetic energy. And this is just to show you that you can transform energy from one form to another. And every time you do that, you lose a little bit of energy as heat. And that energy goes off into the universe and helps to cause it to become more random. Um, Another example of this, okay, of the conversion of energy, you can see that if you've ever been to Las Vegas. When you think of Las Vegas, the first thing you think of are all those lights, right? And you've maybe wondered where the energy to run those lights comes from. And it comes from a spectacular example of converting potential energy to kinetic energy. If you just go a little bit outside Las Vegas, what you'll find is a great big dam called Hoover Dam, uh, which was built several decades ago. And essentially, what we did was we formed Lake Mead. Okay, Lake Mead built up behind Hoover Dam. Here's my little picture here of Lake Mead. There's Hoover Dam right there. And as the height of the water gets further and further above the surface of the earth, the potential energy in this water begins to build. Okay, now inside the dam are structures that are called turbines. Okay, and a turbine is just a wheel, and the axle of the wheel is actually a copper coil. Okay, there's the axle right there. And the wheel itself has magnets in it. Okay, so there's these magnets that are kind of like on the rim of the wheel, and the axle of the wheel is a copper coil. And what happens as the water flows from Lake Mead over Hoover Dam, okay, it spins these turbines. That potential energy gets converted into energy of movement. The turbine begins to spin, and it's an unusual property of a moving magnetic field that when it's near a piece of metal, it induces a current, an electric current. And where does that electricity go? That electricity, here we'll just put a big old arrow, and we'll say electricity, that runs Las Vegas, lights all the lights, and runs all the casinos. That's an example of energy conversion. And we'll put Vegas over here. So energy can be converted from one form to another. Happens all the time. Happens when you play dominoes, right? You set those dominoes up, okay, and they have a certain energy because of their position. And then when you flip one domino, you turn that energy of position into energy of movement, okay? And that movement gets propagated as all the dominoes begin to fall from potential energy to kinetic energy. In chemical reactions, where does the potential energy sit? The potential energy sits in the chemical bonds, okay? And the kinetic energy is in the energy of the movement of the atoms or molecules into each other, okay? So those are where our energy exists. In an exergonic reaction, what happens is that the bond that's being broken has more energy than the one that's being formed, so that extra energy is released, and it's generally released as heat. And this occurs during the breakdown of food that we eat. Okay, we take the chemical bonds in the food that we eat, and as we bust them, energy comes out. And what do we do with that energy? We trap it, and we use it to do other things, to do life activities, to build molecules, to perform anabolic reactions. In an endergonic reaction, the opposite occurs. The bond that's being formed has more energy than the original bond that's being broken. And as a result, to get that reaction to work, we have to put energy into the system. Now, in living systems, the energy that's the easiest to use is called ATP. ATP stands for adenosine triphosphate, and it contains chemical bonds that have a lot of chemical potential energy between the phosphate groups. And the reason for that, as we'll see a little bit later on, is that the phosphate groups have a negative charge. And so to hold two negatively charged groups together, it takes a lot of physical force. And so when you pop those bonds, a lot of energy comes out, and you can use that energy to build other molecules. And so the nickname that I use for ATP is biological gas in the tank. Okay, it's very much similar to the way that you fill up your car and drive to work. Okay, if you look at your car, you could think of your car as a system, just like your human body is a system. And your car uses a form of energy to move from one place to another, and that energy comes from the gas that's in the tank. Okay, the gas is a hydrocarbon. That hydrocarbon is called octane. Okay, it's a chain of 8 carbon molecules hooked one to the other to the other. And the way that your car moves is that the octane eventually finds its way to the carburetor, where gasoline vapor meets a spark plug, and when the spark plug makes a spark, the gasoline vapor and the oxygen in the air will chemically react, and that'll cause an explosion. And that explosion will move pistons inside your engine. Those pistons will turn a shaft that'll eventually turn the wheels of your car, and that's how chemical potential energy that's in the bonds between the octane molecules becomes kinetic energy. The end products are movement, right? Your car moves. And then coming out the back of your tailpipe is carbon dioxide and water. And of course, you lose a little bit of energy as heat. Now, y'all know that gasoline comes from crude oil. Crude oil comes out of the ground, and crude oil is a much bigger molecule. Okay, it's a hydrocarbon that's sometimes 20, 30, 40, 50 carbon atoms hooked to each other. And you can't put crude oil directly in your gas tank. Your engine won't understand it. It won't be able to use it to make your wheels turn. And so we have to process that energy-rich crude oil into a form your energy can understand in order for your car to move. And we do that by taking the crude oil and breaking it into smaller fragments. And it's that 8 carbon fragment octane that makes up the active component of gasoline. Well, how does this work in your body? Well, in your body, the chemical potential energy is in the chemical bonds of the food that you eat. And you can't directly use that energy to do cellular work. You have to transfer it into something that the cells understand in order for you to build biologically active molecules and carry out life processes. And so we take the energy that's in those chemical bonds, we break those bonds, we trap that energy, and we transfer it to ATP, and we use that to do the work of existing, of living. Okay, so one of the concepts we want to address when we talk about how it is that chemical reactions happen is the concept of activation energy, which is defined as the energy needed to break chemical bonds in the reacting molecules so that we can now form new chemical bonds and generate the product. And the kinds of forces that affect the rate of a chemical reaction and as a result cause more collisions between reactant molecules include concentration, temperature, and the presence or the absence of catalysts. Now, in order to visualize this, I want you to imagine the room you're sitting in now as filled with a bunch of red and white billiard balls, okay? And those will represent the reactants of a chemical reaction. And in order for us to form a new compound, what has to happen is that those red and white billiard balls have to bump into each other and stick, and that'll make a new compound that will be a combination of the red and the white billiard ball. And so if we think about these billiard balls kind of moving around, you know, in the room you're sitting in, kind of floating over your head, and occasionally they bump into each other, you can visualize what would happen if we introduced a lot more red and white billiard balls into the room you're sitting in, right? They would probably bump into each other more frequently, and as a result, generate more product more quickly. And that's how concentration affects a chemical reaction. Basically, by increasing the number of reacting molecules, you increase the chance that the reacting molecules will bump into each other, and you increase the rate at which you'll produce the product. Now, temperature is a little bit tougher to kind of get a handle on. Temperature essentially provides movement to the participants in a chemical reaction, causes the reactants to move around more quickly. And so you can imagine now, you're still sitting there in your room visualizing your billiard balls. If we were to heat the room up, the billiard balls would move around more quickly. Well, the more quickly they move around, the more likely they are to bump into each other and form a product. And so concentration and temperature both increase the rate at which a chemical reaction can occur. Now, catalyst is something different. A catalyst is like a third party in a chemical reaction that sort of enters the room and would take a hold of one red billiard ball and one white billiard ball and would force them to bump into each other with just enough force and in just the right orientation to form the new compound. And then once that happens, the catalyst would let go of the product, the red and white billiard balls hooked to each other, and would move on to the next chemical reaction. And so what happens as a result of the catalyst is that the amount of energy required to make the product goes way down. The chemical catalyst, because it does not get consumed by the reaction, is able then to cause one reaction to occur, then the next, then the next. And so this allows chemical reactions to speed up without having to, say, change the temperature or change the concentration of the reactants. And that's why the concept of a catalyst is so important in living systems, because living systems can only tolerate a certain range of temperatures. For instance, the human body likes to exist at about 98.6 degrees Fahrenheit. If it gets too hot or too cold, what happens is that you get sick, and if you get too hot or too cold, you can even die. And so that's not an effective way to try and mediate chemical reactions by producing massive amounts of heat or by changing the concentrations of molecules to a tremendous extent. Instead, these catalysts allow us to work with existing temperature and concentration conditions in order to make enough product that a living cell can use that product to do something. It can carry out life activities. Catalysts in living systems are generally proteins, which are called enzymes. And what they do is they enter the chemical reaction situation and they bind to the reacting components, cause them to interact, form the product, and then the product is released and the catalyst moves on to the next chemical reaction. And so because it's unchanged, it's reused many, many times. Now, there's different classes of chemical reactions that we can envision. In a synthesis reaction, we take two small pieces and we hook them together to make a bigger molecule. In the human body, these reactions are called anabolic reactions. Anabolic means to build up from smaller pieces.
The opposite of this is a decomposition reaction, in which a large molecule is broken apart into smaller pieces. In the human body, these reactions are called catabolic reactions. And the reason that catabolic reactions are such a big deal is because it's these kind of reactions where we actually break a chemical bond between, say, the molecules that make up our food, that energy is released and living cells can use that to do work. So in the human body, we talked about metabolism, right, which is the sum total of all chemical reactions in the body. All metabolic reactions are broken down into either anabolic reactions or catabolic reactions. And the anabolic reactions generally need energy from the catabolic reactions in order to work, because large molecules don't assemble themselves spontaneously. They need a little push from the left-hand side of the reaction in order to go. And that comes from the energy that we extract from the chemical bonds in the food that we eat, which are catabolic reactions. And so this is why you have to eat to live. This is where you get the energy to build stuff that living systems need in order to keep living. In an exchange reaction, essentially what happens is that two molecules switch partners. Here you can see the example AB plus CD gives you the products AD plus CB. These are typical reactions that take place in living systems where we form new compounds from two pre-existing compounds, and the body uses those products in order to carry out some sort of living process. A reversible reaction is one that doesn't have a significant energy barrier between the reactants on the left-hand side and the products on the right-hand side. And so the energy to go either from left to right in the chemical reaction or right to left is available in the immediate environment. And so what happens in these types of reactions that are called equilibrium reactions is that essentially the reaction will settle down to a point at which the rate at which you form the products is approximately equal to the rate at which you form the reactants. Basically, the rates will stabilize. And so what happens is that you have, at equilibrium, a constant ratio of products to reactants. And that ratio is determined really by the reaction itself. It's sort of like an intrinsic property of the reaction. So any equilibrium reaction you can imagine at equilibrium will have a certain ratio of products to reactants. And if you try to change that ratio by adding more reactants or adding more products, what will happen is that the reaction will adjust so that it reestablishes that equilibrium ratio and restores now the initial state. As to take this reaction as an example, let's say that we dumped a whole lot of AC into the beaker where this reaction was happening. Well, that AC wouldn't just sit there, okay? It would dissociate into A plus C, and the ratio of the products to the reactants would then stabilize. Now, there'd be more of each, okay, but the ratio wouldn't change. And the same thing would happen if we tried to, say, load this reaction up with a bunch of A plus C. The reaction would shift to the left, produce more of AC, and the ratio would be restored. Okay, you can break all compounds down into two broad classes: inorganic compounds, which are compounds that do not contain carbon and are usually structurally simple molecules, and organic compounds, which always contain carbon. Often they also contain hydrogen. They generally have covalent bonds, which are very strong, and they're usually large molecules. Now, the reason that carbon is a big deal when we talk about the chemistry that goes on in living things is that carbon has a couple of unique properties that the other elements in the periodic table don't have so much. And that's the ability of carbon to form long chains and also to form rings, or both. And because of that, you can build a lot of very complex molecules using carbon as a backbone. And a lot of molecules that you find in living systems are very complex, large molecules that are based on carbon, like DNA and protein and lipids and so forth. If you didn't have this ability, if you couldn't form rings and chains, it would be tough for you to build enough variety in the molecules that carry out life processes to have life work. Basically, the other elements in the periodic table don't do that extensively enough to form the basis of life as we know it. Now, water is also very important in living system. It's the most important and abundant inorganic compound in any living system. Remember that water is a polar solvent, so it very easily associates with either charged or polar molecules. They dissolve in each other. This is one of the reasons that water has the nickname the universal solvent. Basically, it can dissolve virtually anything unless it's nonpolar in nature. This enables water to provide a medium in which chemical reactions can happen in living systems. Remember what we talked about when we talked about the three states of matter, right? Solid, liquid, and gas. And in a solid, remember that there's not much molecular movement, right? Things just kind of vibrate at a fixed point, and there aren't collisions. And remember that we need collisions in order to produce a product. In a liquid, there's enough energy of movement for molecules to move past each other. And if things are moving, things can bump into each other. And if things can bump into each other, chemical reactions can occur. So water, one of its most important properties, not only does it dissolve a lot of things, but it provides an environment in which chemical reactions can happen. What else does water do? Well, in addition to dissolving a lot of stuff, it also has a very high heat capacity, okay? Meaning that it gives off a lot of heat when it freezes, and it absorbs a lot of heat when it liquefies, and that helps to stabilize our body temperature. This sort of touches on water solvent properties, right? In a solution is basically something that's dissolved in something else. For instance, if we were to look at salt water, okay? You were to dissolve a teaspoon of sodium chloride in a glass of water, the solute would be the salt and the solvent would be the water. Generally, the solute is the component in the mixture, in the solution, that is present in smaller quantity. The solvent is the component that's present in higher quantity. Substances which contain polar covalent bonds and dissolve in water are termed hydrophilic. Okay, now remember, I told you to be on the lookout for words that you might not be familiar with. So if you look at the word hydrophilic, let's break it down, okay? The first part of the word, hydro, means of or pertaining to water. Philic means to be attracted to or to love, okay? So something that's hydrophilic is going to very easily dissolve in water, usually because it has the same chemical characteristics as water. It has a polar or a charged character. Substances that contain nonpolar covalent bonds, things like oils and grease, Crisco, butter, stuff like that, are termed hydrophobic, okay? Hydro meaning water and phobic meaning afraid of, okay? So y'all know, for instance, that oil and water don't mix. And the reason for that is that oil is hydrophobic. It doesn't have a separation of charge if you look at the molecules that make up oil, while water is extremely polar, right? Because it has the electronegative oxygen connected to the two hydrogens, and as a result, the oil is not going to dissolve in the water. They don't share chemical characteristics. The polarity of water and its bent shape allow it to interact with several neighboring ions or molecules, and this is what's called solvation, okay? When you have a solute that's completely surrounded by water molecules, it's said to be fully solvated. And so if you go back to our example of salt water, right, you know that you can dissolve a teaspoon of salt in a glass of water. You can stir it and mix it, and the solution will go clear, right? And so let's say you add 2 teaspoons of salt. Well, that'll probably dissolve in the water as well. Well, let's say you add 25 teaspoons of salt to the water. Well, you're going to get to a point where the salt's not going to dissolve anymore. And the reason for that is you run out of water molecules to surround the salt as it attempts to dissolve in the water. And so the remaining salt just sits there as a solvent on the bottom of the glass. And nothing that you do will change that to any great extent. Okay, so there's always a limit of how much of something you can dissolve in something else. And That limit is actually also a chemical property of a molecule or of an atom. Okay, you can look, for instance, at how much salt you can dissolve in water, how much sugar you can dissolve in water, um, how much gasoline you could dissolve in turpentine, if you want to take a hydrophobic example. Okay, and there's going to be a set amount for each of those. It's again like your fingerprints are a characteristic of you. This is a characteristic of a compound or an atom. Water's role as a solvent makes it essential for our health and survival. And we already talked about the heat capacity, right? This is due to the phase changes that water can go through, and this is one of the ways that water stabilizes our body temperature. And remember that you want to keep the body temperature around 98.6 degrees Fahrenheit, which is 37 degrees centigrade. Because if temperatures warm up too much, then what happens is that those catalysts that make chemical reactions happen in the body, those enzymes that we talked about, they'll kind of unravel, they'll lose their shape, and the chemical reactions that they make work will stop. And when chemical reactions that keep life going stop, life stops, right? So you die, because that's the reason that we can't get too warm. The reason we can't get too cold is if we look at the flip side of the equation, right? What has to happen in order for chemical reactions to occur? Things have to bump into each other. And if you start cooling things down too much, eventually what's going to happen is that the water will freeze, the solutions in the body will freeze, chemical reactions will then stop, life will cease. Okay? So this is why the heat capacity of water is a nice temperature buffer, keeps our body temperature from getting too high or too low. And you can see this if you look at, like, you going outside on a hot day, right? What happens when you go outside on a hot day? Remember from chapter 1, right? You sweat, and that sweat, as it pools on your skin, begins to evaporate. And as the water in the sweat goes from a liquid to a gas, it takes heat with it. That heat gets lost as energy of movement as you vaporize the water. It causes the surface of the skin to cool, and that cools the blood that's at the surface of the skin, and that ends up lowering your body temperature. Okay, so that's an example of water keeping your body temperature from rising too high. If we look at the flip side, and we look at you getting real cold, okay, one of the things that we know is that water will give up heat to its surroundings as it begins to cool down. Okay, this is what's called the heat of fusion. And so the body will take every precaution it possibly can, using the heat capacity of water as a tool to try and keep your body temperature from dropping to the point where chemical reactions slow to a stop. Okay, let's take a look at some mixtures now for a minute. Now, what is a mixture? A mixture is a combination of elements or compounds that are physically blended together but are not bound by chemical bonds. A solution is a substance called, where a substance called a solvent dissolves another substance called the solute, and usually there's more solvent than solute in a solution. A colloid differs from a solution mainly on the basis of the size of its particles, with the particles in the colloid being large enough to scatter light. You don't see too many colloids. A good example of a colloid that you may be familiar with would be Jello, okay, as an example. A suspension is where the suspended material may mix with the solution or the suspending medium for a short period of time, but it'll eventually settle out. Perfect example of a suspension is sand and water, right? You know that you could take.
Okay. One of the aspects that we need to understand regarding solutions is this idea of concentration, which is the amount of any molecule in a specific volume of solution. A percent composition gives the relative mass of a solute found in a given volume of solution, and molarity is a different way to measure the concentration of a solution. It's defined as the number of atoms of a solution in a particular volume, using the mole as a way to compute that. Essentially, remember that a mole of something is 6.02 times 10 to the 23rd atoms, and depending on the molecule or the element that you're talking about, that's going to be a different weight of that particular element or compound in a particular volume. As an example, let's say that we wanted to make a solution, okay, of a particular compound, and let's say our solution was a solution of, oh, let's just for fun take carbon, okay. Remember that carbon has an atomic mass of 12.01, okay, and let's say that we wanted to make a 1 molar solution of carbon. Well, remember what 12.01, this atomic mass down here, indicates. That means that in 1 mole of carbon, I have 12 grams of this particular element. So if I wanted to make a 1 mole solution of carbon, what I would do is I would weigh out 12 grams of carbon, which is equal to 1 mole of carbon, and I would dissolve that in 1 liter of solution. And that's what I would call, if you follow up here, a 1 molar carbon solution. Now, if it were a different compound we were talking about, we would have a different value for the atomic mass that would change now the amount of the compound I weigh out. If we were making, say, a solution of ethanol, okay, instead of a carbon solution, the formula for ethanol is this, okay, COH here and hydrogen there and hydrogen here and same up here, over here and here. Okay, so a 1 molar solution of ethanol would be different because I would have to compute now the molecular weight of this compound. So remember, the carbon has an atomic weight of 12, so for ethanol we would take, for the molecular weight, 12 times 2, which is 24. For hydrogen, the atomic weight is 1, so let's add these together. Say the carbons over here, that's 24. The hydrogens here are 1, 2, 3, 4, 5, 6 total, okay, for the atomic mass. And then finally, oxygen has an atomic mass, if you remember back, oxygen has 6 protons. I'm sorry, oxygen has a total of 8 protons in its nucleus, 8 electrons orbiting its nucleus, and total of 8 neutrons. So oxygen is going to have an atomic mass of 16. Okay, so the atomic weight of a molecule, molecular weight of a molecule of ethanol is going to be 24 plus 6 plus 16. Okay, so that's going to be 30, 46, which is going to equal a total of 46 grams of ethanol in 1 mole. Okay, so if I want to make a 1 molar solution of ethanol, I'd weigh out 46 grams, and then I would mix it with enough water to make up a liter of solution. So it would be 46 grams of ethanol. I'll just abbreviate that ETH. That's 46 there, per liter of solution. That would be 1 molar solution of ethanol. So you can see there's different ways that we can compute this. And you can see here when we're looking at solutions how we can use the mole concept to make solutions of specific concentration, and then we can react those solutions with each other in a ratio that will produce a certain amount of a chemical product. Okay, so that's a couple of ways to compute concentration of solutions. And the reason you need to know that is because let's say in a clinical setting, let's say you're administering a certain compound to a patient, like a medicine. One of the ways that you're going to see compounds expressed is either as percent solutions or as solutions that have a certain molarity to them. Okay, and if you want to compute how much total compound to give to somebody who has a particular weight, you're going to have to be able to compute from these concentration units back to total amount of drug in order to know how much of a particular drug that you want to put in a syringe or um, include in a tablet, and then how many, let's say, tablets that you want that patient to take. Okay, so that dictates the dose. Okay, pH is another type of concentration measurement, and pH measures the concentration of protons in solution using a very special scale. Okay, this P has a definite definition. Okay, so let's run through some of these important points about pH, and then I'll show you how we use the pH scale. The scale for pH runs from 0 to 14, and it's a measurement of the concentration of free protons in solution in moles per liter. pH of 7 is neutral. Distilled water has a pH of 7. pH below 7 is acidic, where the concentration of protons is greater than the concentration of hydroxide anions. pH above 7 is alkaline, where the concentration of hydroxide anions is greater than that of protons, and it's measured on a logarithmic scale. As a result, a change in 1 or 2 or 3 pH units is a change in order of magnitude in the concentration of protons. For instance, a pH of 1 contains 100 times more protons than a pH of 3, and a pH of 8 contains 1,000 times more protons than a pH of 11. You might wonder, well, why is this the case? Well, this is the case because of the definition of P. So if we look at the definition of P, P is defined, little p here, as equal to the opposite of the log to the base 10 of whatever comes after this expression, expressed in molar concentration. So molar concentration, the symbol is big M. So molar concentration of whatever we're talking about here. Okay. In the case of pH, we're talking about the concentration of protons. Okay. So let's put here protons as expressed in units of molarity. Okay. So H plus. It's a little tough to read. Okay. Okay, well, how does this evaluate when we actually carry out the math? Kind of interesting. Let's say that we have a solution that is 10 to the minus 2 molar in protons. Okay, this might be an acidic solution here. A 10 to the minus 2 molar proton solution would have a pH of 2. But why is that? Well, because we have to evaluate this expression here, okay, this 10 to the minus 2, and look what happens when we evaluate it. Remember that P is equal to the opposite of the log of whatever comes after P in molar concentration. Well, here, the molar concentration is 10 to the minus 2 of protons. So the pH for the solution is going to equal the opposite of the log to the base 10 of the quantity of this solution here that I've written, 10 to the minus 2. So the way you do this expression on your calculator is you take the log of 10 to the minus 2 first, which is going to equal minus 2, and then you take the opposite of that in sign. Okay? And the opposite of that in sign will make that evaluate to 2. Okay? So a 10 to the minus 2 solution of protons is going to have a pH of 2. A 10 to the minus 3 solution of protons is going to have a pH of 3. A 10 to the minus 7 solution of protons is going to have a pH of 7. And so you can see that the bigger the pH number, the smaller the proton concentration. That's how it's going to evaluate on this scale. And you can also see that for every single unit of change in pH, it's a tenfold change in the concentration. So that's how we go up and down the pH scale. And that's why these statements down here make sense. Okay, a pH of 1 contains 100 more protons than a pH of 3. Well, what's the concentration in protons if something has a pH of 3? It's 10 to the minus third. What's the concentration of something that has a pH of 1? It's 10 to the minus 1. Okay, and you can see that those expressions differ by an order of magnitude of 100. Okay, so this is just another way of measuring concentration. In the case of little p, the most common use is to measure proton concentration, and this is a measure of what we call acidity. Basically, the tinier the pH number, the more acidic the solution. The larger the pH number, the more alkaline the solution, with 7 representing the neutral state. Okay, and the neutral state is defined as 7 because that's the rate at which water spontaneously comes apart. In any solution of water, okay, a certain number of molecules is going to come apart, and they're going to form now. Let's draw this equation that lies very far here to the left. Okay, these ions, H plus and OH minus. And the rate at which that happens in a glass of pure water, as an example, is 1 times 10 to the minus 7th molecules per 6.02 times 10 to the 23 total molecules. Okay, so that evaluates to a pH of 7. And that's why that's defined as neutral, because that's what's going on in regular water. Now, if we add an acid to it, that acid will kind of fall apart, okay? Molecules that are acids have a proton, have a hydrogen atom in them that is easily lost as an ion, as a proton. And when that occurs, you're adding protons to the water solution, and as a result, you're causing their concentration to go up, which means you're causing their pH to go down. Base, on the other hand, is defined as something that will bind to protons in regular water. So when that happens, when you throw a base into a solution, the amount of protons decreases. As a result, the pH will go in the opposite direction. It will begin to climb. Okay, so remember, acidic is lower than 7, basic is higher than 7. Now, in the body, you don't want pHs to change very much, okay, because if they do, it's going to screw up the molecules that carry out the life processes of the human body. It's going to screw up the enzymes. And so what we use in the human body to keep this from happening are special solutions called buffer solutions, which contain a pair of related molecules. One is a weak acid, and the other is what we call, it's in chemistry, it's conjugate base. Okay, so you'll have a solution here. Okay, let's say this is a beaker of a buffered solution. Okay, there's the liquid interface, and in the solution, if we looked inside it, okay, what we would see is a couple of components. We'd see this weak acid, all right, and we would also see its conjugate base, okay, which we would define as the acid without the proton attached, and so it would have a negative charge. So these guys are just kind of floating around in solution. And what happens, let's say that we throw in a very strong acid as an example, okay, like hydrochloric acid, that's stomach acid, into the solution. We challenge this solution. Well, normally, if this were pure water, what would happen is that the hydrochloric acid would ionize. I'll show that down here, come apart and form a proton and a chloride anion. Okay, and it would do that, very quickly. And these free protons, remember, are going to add to the total proton concentration of the solution, and the result now is that the pH would drop real quick. But in a buffered solution, what happens is that we have some of this species here, this base, floating around. What will happen is that the base will sort of come to our rescue, and it'll combine with these protons that are coming in here from this strong acid, and it'll form now this weak acid. Now, weak acid, by definition, is not going to dissociate as much in solution as a strong acid will. And so basically, these protons that we threw in here when we introduced this hydrochloric acid are going to be like locked away in prison, okay? And their prison is going to be bound, to this base. Once this happens, once these protons are part of a weak acid versus a strong one, a weak acid doesn't dissociate as much as a strong acid does. It doesn't come apart as much in solution. And so the change in pH is going to be negligible. So you would normally expect in a water system for the pH to drop a lot if we added a strong acid, but in a buffered solution it doesn't change hardly at all, because these molecules are in here waiting for the challenge. Okay, now let's say that we take a different approach here. Let's say that we challenge this in a different way, and instead of adding now a strong acid, we add a strong base. Okay, so let's go over here, and we'll just use a different color. All right, we'll use red. Okay, so we got our buffer system still in the solution. It's just kind of hanging. Okay, And there's our HA plus and our A minus still in solution. Okay, and here comes this strong base. Okay, so an example of a strong base would be something like oven cleaner, sodium hydroxide. So we throw that into the solution. Normally, if this were just pure water, what would happen is that the sodium hydroxide, when we threw it in here, okay, would dissociate into hydroxide anions and sodium cations. Okay, it's a strong base. That's what a strong base does. And as a result of that, what would happen is that the hydroxide anions would be attracted to what few protons there are in distilled water. And they would form water molecules as a result, but the loss of free protons due to the introduction of the base would reduce the number of protons so much that the pH would begin to climb quite a bit. Okay, the pH would go way, way up. And as a result, the solution become very alkaline. Okay, but when you've got a buffer system, what happens is that, again, the buffer system comes to our rescue. And so when you throw the strong base in here, what happens is that this time now, these protons that are part of this portion of the buffer system, they combine with the hydroxide anions and they form good old water. Okay. As a result, these hydroxide anions don't get an opportunity to steal protons from the water part of the solution. Instead, they steal the protons from the weak acid. Okay, the weak acid will give them up more readily to the strong base than the water will. And the result is going to be now a solution whose pH doesn't change very much. Okay, normally you'd expect it to go up quite a bit with a strong base added to this water solution. In this case, in the buffered solution, that doesn't happen. And so basically what a buffered solution does with a challenge to its pH is it keeps the pH from changing significantly. Now the reason that this is important in living systems is because you don't want your pH going way up or way down, because you'll screw up enzymes. As a result, that'll shut down chemical reactions, and eventually that can result in the death of cells, which results in the death of tissue, which causes organs to die, which eventually would kill you. Okay. The other thing that changing pH screws up in the human body is it screws up membrane potential. Remember that membrane potential is that energy that's stored as a result of the separation of charge across cell membranes. And pH, because it represents an introduction of charged particles into a solution, changing the pH will change the distribution of those charged molecules across a membrane and cause membrane potential to get messed up. Okay, and if that happens, systems in the body that rely on electrical signals to work, like muscle contraction and nerve transmission, will shut down. And if that occurs, you'll die, right? If nerve transmission shuts down, your nervous system will quit working. That's your brain and your spinal cord. And if muscle contraction shuts down, the ability for muscles to squeeze will shut down. And so the most important muscle in your body to keep you alive is your heart. So your heart would stop. So this is why buffered systems in the human body are important in maintaining homeostasis. And there's a lot of different buffer systems in the body. The protein buffer system is one system. The bicarbonic acid system is another one. The phosphate buffer system is another one. There's quite a few of them. And some of them even operate together. Okay, so we can buffer solutions over a very wide range. Okay, so this is an important chemical concept here. Okay, remember that the molecules of living systems primarily are based on carbon, and we can attach what we call functional groups to these carbon-based molecules and change their characteristics. Different groups that we can attach to carbon skeletons include ester groups, amino groups, carboxyl and phosphate groups. Very large molecules are called macromolecules. Macro means big, okay? They can also be called polymers if all the building blocks are the same or very similar. Examples of biological polymers include proteins, which are polymers of amino acids, and DNA, which is a polymer of nucleotides. Isomers have the same molecular formulas, but they have different structures. So the difference between two isomers is that the chemical formula might be the same, but the way the atoms are hooked to each other might be different. And as a result, these compounds might have slightly different chemical properties. Okay, carbs provide most of the energy for the human body, for living systems. They're needed for life, and they include sugars, starches, glycogen, and cellulose. Of these, the human body can only digest sugars, starches, and glycogen. Cellulose, we know better, is wood, and that part of our diet is what we call fiber. That passes right through our digestive system and is not broken down. As a result, it becomes part of the waste material. It's also fuel for the bacteria that live in our large intestine, which is kind of nice because for the bacteria, that provides a source of energy, while the byproducts of that bacterial metabolism are compounds that we need in order to live. And these include byproducts such as vitamin K, which are important for processes like blood clotting. Some carbs are converted to other substances which are used to build structures and to generate ATP, and other carbs function as food reserves. Carbs are split into three major groups based on their size: monosaccharides, disaccharides, and polysaccharides. And you're looking here at some of these different types. This is how we would form a disaccharide from its two component building blocks, monosaccharides. And in order to do that, we have to form a novel bond between these two monomers, okay? And so we remove the components of a water molecule in dehydration synthesis, and we begin to build now what could eventually be a polymer. Here we go from two monosaccharides to one disaccharide. And so in the human body, a particular enzyme will carry out this reaction, and then we might store this molecule once it gets long enough as temporary fuel in the body. The reverse reaction might be carried out in another tissue in the body, say living cells that need this for work, and we'll take this molecule and we'll split it by using a water molecule to cut this bond and forming now the two monomers. And the monomers then might be available for energy for living cells. These two reactions are never going to happen in the same place at the same time in the human body, because if that were the case, we would engage in what we call a feudal cycle, where we hook two components together and we turn around and immediately take them apart. Generally, the physical location and the enzymes that carry out this forward reaction are different than the ones that carry out this reverse reaction. And just in point of fact, um, you may not have seen this representation of molecules before. This is a shorthand that chemists use to try and very quickly draw carbon-containing compounds that have a lot of functional groups hooked to them. In this case, carbohydrates. If you look down here, what you see is the long version of this molecule, okay? And you can see here all the carbons and all the attached groups. Remember that carbon can form 4 bonds. So you've got 1, 2, 3, 4 bonds here, 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 and here. So that satisfies that requirement that carbon has to form 4 bonds and as a result fill its outer shell. Okay. The hydrogens can form a single bond and fill their outer shell. Oxygen can form 2 bonds to complete its outer shell. And so you can see, if you look at this molecule, that all those requirements are met. So this is a stable molecule here. But for a chemist, sometimes we like to abbreviate this so we don't show the carbons, we just imply that the carbons are there by putting a bend in the molecule, and we only show the functional groups, and so that translates to looking something like this. Okay, um, so as we draw organic molecules, we'll use some of these shorthand methods to represent them because it's just easier to draw. Okay, instead of drawing in all these atomic symbols. So disaccharides come from the combination of two monosaccharides together by dehydration synthesis, such as when we take a sucrose and a glucose molecule, we hook them together. I'm sorry, we take a glucose and a fructose molecule, we hook them together to form sucrose. If we split sucrose apart, we form glucose and fructose. Maltose is made up of glucose and glucose, and lactose is made up of a glucose molecule hooked to a galactose molecule. And again, in the human body, we can take these disaccharides apart, okay, going in this direction, right to left, or we can form them going from left to right. And the compartments in the body that do the building and the tearing down are going to be different physical locations. Polysaccharides are basically chains of monosaccharides hooked one to the other to the other. And in the human body, this represents a way of storing energy to use later. The major polysaccharide that's stored in the human body is called glycogen, and it looks very much like this cartoon here, where these are chains of glucose molecules that branch, okay, and all of these glucose units are hooked together by those bonds that are created by dehydration synthesis. In the food that you eat, the major polysaccharide is starch in vegetable material and glycogen in animal products, such as meat. And when you consume these, what happens is we have the enzymes present in our digestive system to break these bonds down and absorb these individual sugar units directly across the lining of the intestine into the bloodstream, where they head to the liver, okay, big organ that sits in your right upper quadrant of your abdominal pelvic cavity, that has as its job to either take this fuel that's in the blood and store it for later use in the form of glycogen, shown here, or as fat, which is a fundamentally different molecule we'll talk about in a minute, for later use so that you can use calories between meals. Or if your energy needs are high enough, it'll pass that fuel that you've absorbed from the gastrointestinal system into the blood onto the rest of the body so you can immediately use it for energy. Okay. Um, when your blood sugar levels drop, okay, between meals, one of the things that your liver will do is it'll take the stored glycogen and it'll start splitting off these sugar units and putting them into the blood, where they head to the body to be used as energy. Okay, um, if your blood sugar levels get really high, your liver will send out a special chemical signal called insulin that'll tell the cells in the body that there's sugar around and that they should use it. They should take it out of the blood and use it for energy. Uh, and at the same time, the insulin will promote in the liver the act of glycogen synthesis. And so we'll take sugar molecules and form this temporary polymer um, to basically store the calories that the body can't immediately use at that time. Okay. Remember that in carbohydrates, as well as in fats and in protein, the major components, the major macronutrients in our diet, there are there's an amount of energy called calories that's a characteristic of each of these macronutrients, and so they represent chemical potential energy that the body can use for work. And of the three, okay, lipids have the most calories per gram, carbs have the second most, and proteins have the least. And so this is why a lot of health advice with regard to your diet concerns the reduction in the amount of fat that you consume, because fat has a lot of calories, and if you eat a lot of calories, it's likely that you're going to have to store a lot of calories as glycogen or primarily as fat. So if you eat a lot of fat and you don't do a lot of activity, you're going to get fat. Okay, so that's uh, why it is we gain weight when we eat more calories than we actually burn. Okay, so let's talk about lipids. Lipids have the most calories per gram. They are similar to carbohydrates in that they're based on carbon. They contain hydrogen and carbon and oxygen, but they contain them in different ratios than carbohydrates do. Uh, in carbohydrates, you have a 2-to-1 ratio of hydrogen to oxygen in the carbon molecule. In lipids, that ratio is much higher. Okay, so there's a lot of carbon-hydrogen bonds in lipids. They have very few polar covalent bonds, so as a result, they are hydrophobic, and so they don't mix well with water. They tend to associate with other fat molecules, other lipid molecules instead. They're mostly insoluble in polar solvents. They combine with proteins in order to be transported in the blood if we need to use them as fuel. The major lipid in the human body is the triglyceride. Um, they provide protection, insulation, and energy as a uh, as a storage molecule. We know triglycerides better as fat. Okay, at room temperature, triglycerides can be either solids or liquids. They provide more than twice as much energy per gram as carbs or proteins do, and their storage is virtually unlimited. It's the only ceiling to their storage is weight gain to the point where you die. Okay, you get so heavy that the body can no longer function. Excess dietary carbs, proteins, fats, and oils will be deposited in the body as primarily excess fat. Now, why is this? Why do triglycerides and lipids in general have so much more energy in them than carbohydrates or than amino acids do? And the reason for that is shown right here. Okay, look at the number of carbon hydrogen bonds in a triglyceride. This whole thing is a triglyceride. Okay, it's formed in the human body by the combination of 3 fatty acids. This part here that I'm circling is the fatty acid part. Okay, this one here is a fatty acid, this one here is a fatty acid, and this one down here is a fatty acid. And they combine with the molecule of glycerol, which is an alcohol molecule, has 3 hydroxyl groups hanging off each carbon, and through dehydration synthesis, we generate this large molecule. Okay, but notice all the carbon hydrogen bonds here. If you count them, there's tons of them, and you compare that to 3 slides ago when we were looking at carbs. The number of carbon hydrogen bonds is a lot fewer, and you can basically assign the calorie content of any molecule by counting the number of carbon hydrogen bonds. The more carbon hydrogen bonds there are, the higher the calorie content. The fewer carbon hydrogen bonds there are, the less the calorie content. And so this is an illustration of why when you eat a lot of fat, you get fat, because there's a lot of calories contained in these chemical bonds, a lot of chemical potential energy. Okay, now occasionally triglyceride will have a fatty acid chain here that has a double bond in it. Notice the double bond here. And notice when there's a double bond, you lose a couple of hydrogen atoms, and that's called an unsaturation. And so maybe you've heard of oils or fats that are polyunsaturated. That means that they have lots of double bonds in their in these long fatty acid chains. That represents fewer calories because there's fewer carbon hydrogen bonds. There's fewer calories in the polyunsaturated fats or oils, and as a result, when you use them, when you consume them or you use them for cooking, your food is going to have fewer calories. As a result, it's going to be healthier for you to eat. Okay. Um, Another thing to notice about the triglyceride is that there's very few electronegative atoms in it. Right. These right here are the only oxygens. Okay. The rest of the molecule is basically all carbon-hydrogen bonding. And so this is why it's hydrophobic. It's not terribly polar because there aren't very many electronegative atoms compared to the whole molecule. And so these tend to be um, uh, greases and oils, okay, at room temperature. And so what they'll do in the human body is they'll associate with each other um, and form now a layer of tissue called adipose tissue that the body uses for fuel storage, for padding and protection, and for also insulation. Okay, so that's the story on triglycerides. Now, sometimes we use these molecules not just as fuel or as insulation or protection. We can use triglycerides also to form structural molecules that are part of living systems, and one of the major ones are the phospholipids. Okay, and the phospholipid is basically a modified triglyceride that has one portion of it that has a charge, and the other portion which is nonpolar. Okay, and a part that's charged generally is associated with a phosphate group and maybe some nitrogen groups as well. And the fatty acid tails, as we already know, are nonpolar. And so what you get when you put together a phospholipid is a molecule that looks something like this. Okay, and here you can see kind of a cartoon of the phospholipid. This would be the polar head, and this would be the nonpolar tail hanging off of it. And so what you have is a molecule that's pretty big, that has one part that's greasy, okay, the part that's here in gray, and another part that's charged, the part here in aquamarine. And so in a water solution, what it'll do, in order to obey the second law of thermodynamics, is arrange itself so that the greasy stuff is near the greasy stuff and the polar stuff is near the water. And so what you form in living systems is something called a phospholipid bilayer, which is a major component of cell membranes. And this is important because the cell membrane, as we're going to see in the chapter on cell biology in your book, forms a barrier between the outside world and the inside of the cell, which is semi-permeable, meaning that certain molecules can pass through it and other molecules can't. And so this is one of the ways that the cell not only keeps all its inside stuff inside, but also a way that the cell regulates what goes in and comes out so that the living system keeps on living. Okay, steroids are another type of lipid. Um, they are basically formed by fusing four carbon atom rings together, and we'll show you a picture of it in a minute. Steroids form the basis of the sex hormones, the bile salts, many of the vitamins that we need in our diet in order for certain enzymatic reactions to happen, and they form the backbone of cholesterol, which serves as a component of cell membranes and also as the starting material for synthesizing other steroids. Basically, um, cholesterol is one of the ways that um, living systems regulate how much their cell membranes move around. Okay, if you look here at the previous slide, and you look at this bilayer here, um, there is some movement in the bilayer. These molecules can move from side to side on either side of the cell membrane, and the way that living systems modify that movement is by putting cholesterol in the cell membrane. The more cholesterol you've got, the less side to side movement there is, and the less cholesterol you have in the cell membrane, the more side to side movement you've got. And so this is a look at what the cholesterol nucleus looks like, and you can see there's the four fused rings, 1, 2, 3, 4. Okay, and you can see some functional groups hanging off of there, and depending on what functional groups you put on this basic structure, you'll form different molecules. For instance, this is what testosterone looks like. This is the major male sex hormone. This is what cortisol looks like. This is one of the hormones that regulates our blood sugar. And you see they're not that terribly different, but these few different little functional groups that you add will change the way that this molecule interacts with other molecules that use it in chemical reactions or that respond to it as a chemical signal. Um, Most of these are proteins. So, very important molecule in living systems, the, uh, the, the cholesterol nucleus. Okay. Okay, proteins are basically the workhorse of the cell, and they're made up of building blocks called amino acids, which come in 20 different flavors. A dipeptide is formed when you combine two amino acids to each other through dehydration synthesis, and this forms a special kind of chemical bond called a peptide bond, which we'll see in just a minute. And polypeptide chains are when you hook together 10 or more of these amino acids in a long chain, and this forms a special molecule called a protein. And so, how do you make a dipeptide bond? Um, what you do is you take two amino acid monomers. This is the structural formula for an amino acid here. What I'm drawing my tracing around with my arrow. Okay, and you can hook one amino acid to the other by causing them to interact, front to back, and generating now this novel chemical bond when you remove the components of a water molecule. This is another dehydration synthesis. And this bond here in red between C double bond O and NH in the context of this long chain is called a peptide bond. Okay? A peptide bond is a type of covalent bond. It's formed by dehydration synthesis. These polypeptide chains can contain between 10 and 2,000 amino acids. Now remember that I told you the amino acids come in three broad groups. Okay, the three broad groups of amino acids are polar amino acids, nonpolar amino acids, and charged amino acids. And you can hook these amino acids together in living systems in any order, and you can produce chains of any length. And when you do that, what happens is that you have now these different side groups. Okay, this is where the side group would be in an amino acid. The side group can be any of a number of 20 different functional groups. In this case, this dipeptide we're forming is the result of the combination of two nonpolar amino acids here. The side chain for glycine is simply a hydrogen molecule. The side chain for alanine is a methyl group. Okay, and as you build this long chain, what will happen is it'll begin to take on um, different shapes, different protein structures, and as a result, um, it will form something, a molecular tool that's useful to a living system. It might form the shape of a particular enzyme or the shape of a particular membrane receptor, just to name a couple of examples. And what those will do is carry out certain tasks for the living system. And so this is a way to build molecular tools that keep living systems operating. Okay, so proteins can fall into different levels of structural organization, and these include primary, secondary, tertiary, and quaternary structure. The resulting shape of the protein influences its ability to recognize and bind to other molecules. When we interfere with that structure, the shape of the molecule is messed up, and this is called denaturation. And when that occurs, the protein can't carry out its job anymore. And the kind of components that can affect protein structure, can denature proteins, include heat and changes in salt concentration and changes in pH. And this is why in the human body we need to keep those variables, those measurable characteristics within tight limits, because if we don't, proteins will denature and the reactions of living systems will cease to exist. So in the next series of videos, the next three blocks of videos, you're going to see how these levels of protein structure get put together. Okay, so watch these next three blocks and you'll understand a little bit more why it is that proteins can do so many things in living systems and can carry out so many different chemical reactions. So take a listen.
Proteins are polymers of amino acid monomers. Every amino acid contains a central carbon atom bound to 1. An amino group, 2. A carboxylic acid group, 3. A hydrogen atom, and 4. A group that differs from one amino acid to another and is represented by the letter R. This dehydration synthesis reaction has created a protein consisting of 4 amino acid monomers.
Okay, enzymes are catalysts in living cells that help chemical reactions happen without the need of changing concentration or temperature significantly. They're highly specific in terms of the substrate that they interact with, and they're subject to a lot of different controls in the cell. Their activity can be speeded up or can be slowed down depending on the cell's needs. They speed up chemical reactions by increasing the frequency with which reactants collide, and as a result, the rate at which products are made, by properly orienting the molecules and helping the chemical reaction occur. And so here you can see a cartoon of how that happens. Okay, essentially, here's the enzyme. Okay, this is what is an area on the enzyme, which remember is a protein, a long polypeptide chain, where the chemical reaction is going to happen. Okay, what happens is that we bind now the substrate, which is the molecule whose chemical reaction we're going to help happen, and then we will facilitate the reaction. In this case, we're going to hydrolyze a disaccharide here. And what results now is that we split the molecule, in this case, releasing the products, which are a couple of monosaccharides. And now look what happens once we release the product. The enzyme is free to carry out the reaction again. Okay, and so you don't need many enzyme catalysts to really speed up a chemical reaction significantly. And every enzyme is going to catalyze one and only one chemical reaction in the body. So you've got millions of different enzymes inside each cell carrying out thousands of different reactions simultaneously. Some help catabolic reactions happen, so they break things down, like in this illustration. Others build things up from tinier pieces, okay? So they would take monomers, say, and hook them together. And because they're so good at what they do, they lower the activation energy to get the reaction to go to a tiny enough level that we don't have to really radically change the body's temperature or the body's pH in order to get these reactions to go. So this makes chemistry happen quickly enough in living systems that it makes products that are useful to the human body. Now we're going to finish up by talking about some of the most important molecules in living systems. DNA and RNA are basically information molecules. They're large organic molecules that have carbon, hydrogen, oxygen, nitrogen, and phosphorus in their structure. DNA forms the genetic code inside each cell and as a result regulates most of the activities that take place in our cells through our lifetime. It's like the body's blueprints. RNA is basically a copy of the instructions from a certain stretch of DNA that can relay those instructions from the nucleus of the cell into the cytoplasm, where special cellular structures called ribosomes will use that set of uh, instructions to build a particular protein that'll carry out a particular job for the cell. The basic units of nucleic acids are nucleotides. They're composed of a base, a sugar, and a phosphate group. And we'll see a picture of a nucleotide here in just a bit, and I'll explain a little bit to you the significance of these nucleotides. RNA differs from DNA. It's single-stranded. It has a ribose sugar instead of a deoxyribose sugar in its backbone, and it has uracil as one of its nitrogenous bases instead of thymine. Types of RNA within the cell carry out different functions. Messenger RNA is basically a copy of certain sets of instructions that lie in DNA called genes that contain the information to build a particular protein. Ribosomal RNA is a structural component of the ribosomes, and those are the protein builders in the cell. And then finally, transfer RNA is a type of RNA that is able to carry amino acids with it and bring them to the ribosome when it needs those amino acids in order to build a new protein. And so these nucleotides that we've been talking about that are the building blocks of RNA and DNA, they look like this. Okay, this is one of the four nucleotides. Okay, this happens to be ATP. The other nucleotides for RNA are CTP, GTP, and UTP. And the difference in this first part, this is the part that designates the base. Okay, the base is this part here in green. Okay, so this can be in RNA adenine, uracil, cytosine, or guanine. Okay, and the only thing that will change in the nucleotide is the identity of the thing here in green. The TP stands for triphosphate. Well, where does that part come from? That part comes from these groups here, these three phosphate groups that all have a negative charge and are all held together by these very high energy bonds. Okay, the reason these bonds have so much energy in them is because they have to attach chemical groups to each other that have the same electrical charge. And remember that particles that have the same electrical charge tend to push off on each other, and so to hold them together you need a lot of power. And so when you split these bonds off of the molecule, you release a lot of energy, and so you can do a lot of work. The only difference between the nucleotides that make up RNA, they look like exactly what we've shown here, and the ones that make up DNA is that one of the groups down here on the sugar part, the part here in purple, is simply a hydrogen instead of an OH group. Okay, so in a nucleotide, what you've got is different molecules, different carbons that are designated by their position from the oxygen here in this ring. Okay, and so if we use the numbering system, we have here a a series of carbons numbered 1, 2, 3, 4, and I'm sorry, numbered, got to count it correctly here. 1, 2, 3, 4, and this is what's called the 5' carbon. Okay, so watch again. This is the 1' carbon, the 2' carbon, the 3' carbon, and the 4' carbon. This is the 5' carbon here. Okay, and so what these monomers represent is a building block that isn't symmetrical on all sides. It has ends. Okay, it has a 5' end, which is attached to a phosphate group, and it has a 3' end, okay, which is attached here to a hydroxyl group. And in DNA, the only difference is that the building blocks here have a single hydrogen instead of an OH group. So what you see in the building blocks of RNA and DNA is that the energy is actually built into the monomer. So the energy to build long chains of these, this whole thing is the monomer, okay? Long chains of these things is actually contained in the monomer itself. So as we hook these chains of nucleotides together, we split this bond right here, and when we do, we release energy, and that energy is used to actually make the molecule, to make the RNA, to make the DNA, which is kind of cool, okay, because the building blocks for the information molecules have the information already built into them. Now, that said, we've talked a little bit about biological gas in the tank earlier in the presentation, and I told you that I defined that as a kind of a nickname for ATP. The energy in ATP is contained in these little red bonds here, okay? This is the kind of energy that the body can immediately use in order to do work. And so when we split these bonds, we're able to do things like build big molecules or to move. And so when we eat, when we consume chemical potential energy in our food, we split the high energy bonds in the carbohydrates, in the fats, and in the amino acids, and we trap that energy and shift it over to the phosphate bonds that are part of these ATP molecules. Okay, the energy goes from our food into these chemical bonds, and so we can use that to immediately carry out work in the human body. So this is what biological gas in the tank looks like, and this is where the energy actually sits. Okay, so the metabolic reactions in our body that are catabolic steal the energy from the food that we eat and transfer it over to this special molecule that can be used to make chemical reactions happen that normally wouldn't. So when we hydrolyze ATP molecules, when we split those phosphates off, energy comes out and we can use that to do work. Okay, this leaves behind an ATP molecule which we can turn around and turn back into an ATP molecule as long as we continue to eat. Okay, as long as we continue to take in food. And so we're continuously breaking down and regenerating ATP as we consume energy. The energy that's contained in a single glucose molecule in the presence of oxygen, which is in the air that we breathe, can be used to make between 36 and 38 molecules of ATP. If we don't take in oxygen, we can only make 2 molecules of ATP per glucose, and that's not enough to run the human body. So this is why, ultimately, you have to breathe to live in addition to eating, okay, because we have to have enough energy in order to carry out life processes. And we'll get more into that aspect of living systems when we talk about the cell and we talk about how all these molecules work together. Okay? All right, so that's all I've got for the chemistry chapter. Review this material, not so much because you're going to be tested on it, but it's going to be part of what we learn about in later chapters. Okay, so you might want to come back to this podcast and reference it several times if we come across something in the subsequent chapters that's chemical in nature that you need sort of a refresher course on. So sort of keep this podcast in your hip pocket, okay? All right, I'll see everybody in class.
Take sand and you can throw it in water, you can shake it up, and you'll have a temporary mixture. But if you let it sit, what will happen is that the sand, because it doesn't dissolve in the water, will settle to the bottom, and you'll have your original condition again.